So we've been talking about light and its properties, and also about how it can be a wave and a particle. That's a little bit confusing at times. And so now we're going to look at how light interacts with elements. So when atoms or molecules absorb energy, that energy is often released as light energy. And again, I forgot to, there's, do you notice there's a comma here and then nothing after it? I have no idea what's supposed to be there. I think maybe it's just no comma. So matter absorbs energy, okay? Law of conservation of energy says that, well, the energy content of the universe is constant. So if it absorbs energy, that energy has to go somewhere. And so it will be absorbed and then released later, and often that happens in the form of light energy. And we see examples of this all over the place. Fireworks are an example of atoms being excited and emitting light energy. Neon lights, such as this one, that is actually neon gas, which is being excited by an electric potential, and then it emits that energy as light. And we're actually going to see a neon tube today. Each element exhibits or emits a characteristic color. Here we've got a mercury lamp, a helium lamp, and a hydrogen lamp. And they have different colors that they emit, and those colors are characteristic of that element. Doesn't matter who makes it, when, or how, that they're going to emit the same colors. Now we saw that when light is emitted, when light is passed through a prism, we get a rainbow. We're all familiar with that. When you take the light that's emitted from these elements and pass it through a prism, instead of seeing a continuous rainbow, you see particular lines of color, and in between there's nothing. And that's called an emission spectrum. It's not continuous. There's dark and light parts of it. And that can be used to identify an element, much like a fingerprint can be used to identify a person, or a barcode to identify a product at the grocery store. This phenomenon cannot be explained by classical physics, the physics that we're familiar with of large objects moving in a deterministic way. So this is what those spectra look like. So if we take a hydrogen lamp, pass the light through a slit just to make it a narrower beam, pass it through a prism, normally if we were taking sunlight, we would see a continuous rainbow here. But instead of a rainbow, we see three distinct lines, and in between nothing. And these lines have colors, and the color falls in the same place that the color would fall if it was white light. So if we look down, oh, that one's reversed, isn't it? Yeah, those don't line up very well. That's unfortunate. So that's what the hydrogen spectrum looks like. This is helium. Helium has more lines. Barium has even more lines. This is what you see with sunlight, a continuous spectrum, a continuous rainbow. So scientists observed that this happened, and then, of course, they've got to try to figure out what's going on. Why does it do that? That's not what you expect. And here's oxygen and neon, and we see that they have even more lines. Any questions yet? You can also do sort of the reverse, and instead of looking at the light that is emitted, you can look at the light that is absorbed by a substance. And so here's the emission spectrum for mercury, and here's the absorption spectrum. So here, the mercury is absorbing these colors as light shines on it. And there are different types of instruments that can be used to do that. We also see colors when you put elements in a flame. So here, the heat of the flame is exciting the atoms. It's putting energy in, and the energy is being released as a color of light energy. For sodium, we get this very distinctive yellow-orange color. Potassium is lavender. Lithium is this intense red. Barium can be hard to see. It's kind of a greenish color. But these are the same colors that you will see if you put them in a tube and excite them with electricity. They're characteristic. So Johannes Rydberg looked at these different spectra and tried to figure out a pattern. And so he's looking at it in terms of math, and he's like, there's got to be some sort of a pattern in this. I can't even imagine trying to figure this out. So each of those lines that you see has a particular wavelength, right? And then from the wavelength, you could calculate the energy, the frequency, etc. So he figured out this equation. 1 over lambda equals a constant times 1 over m squared minus 1 over n squared. So m and n are integers, whole numbers, 1 and 2 or 3 and 5, or etc. And he found that this equation worked and described the lines that we're seeing. So awesome, but it doesn't give us any insight into why that happens. So it doesn't tell us why. It doesn't tell us why atoms are stable. We don't even know why his equation works at this point. So yeah, you did that. Great. To understand why it works, we have to look at the model of an atom. So Rutherford's nuclear model, yeah, that's a new word. Rutherford's nuclear model of the atom. Okay, so we've got a tiny dense center called the nucleus, and essentially all the mass of the atom is in there. The nucleus is positively charged, and then we've got some negative electrons that are moving around in the empty space around that. So we covered that in an earlier chapter, nuclear model. So now we're going to be investigating, well, what's going on with those electrons? So there's some problems with Rutherford's model. So electrons are moving charged particles. And according to classical physics, if you have a moving charged particle, it gives off energy. That energy has to come from somewhere. If it's just moving and giving off energy, the atoms should probably glow. We should be able to detect that energy being released from them, but we can't. And this predicts that the electrons would eventually lose energy. As they're losing energy, they'd run out of energy and they would crash into the nucleus. Much like, if you sent up a satellite into orbit and you didn't get it into the correct orbit, gravity would eventually pull it down and it would crash. So the nuclear model was fine as far as it went, but it doesn't explain what happens with the electrons and what happens when atoms gain or lose energy. So along comes Niels Bohr, and he develops a model to explain what's going on with these energy transitions. And in his model, and this model is the simplest to understand because it is like our solar system. And we've all, studied the solar system. You've got the sun in the middle, and the planets rotate around in their orbits, right? We're all okay with that. So in Bohr's model, the electrons are traveling around the nucleus in circular orbits like the planets around the sun. It's like, okay, we could envision this. It's almost like a miniature universe or something. The orbits exist at specific fixed distances from the nucleus. Okay, well, that's like the planets. There are certain distances from the sun. The energy of each orbit is also fixed or quantized. The amount of energy in the atom is related to the electron's position in the atom. So there are different orbits that the electron could be in. And depending on which orbit the electron is in, it will have a different energy. Each of those orbits, though, has a specific amount of energy. When we say something is quantized, we mean there are particular amounts that you can have. And there are many quantized things in everyday life. A set of stairs is quantized. You can stand on the first step or you can stand on the second step. You can't stand in between the steps. The rungs of a ladder. You can stand on the first rung or the second rung. There's nothing in between. You can't just suspend yourself. Grades in school. You're in first grade or you're in second grade. There's no 1.5 grade. Okay? Our monetary system. There's a $1 bill, a $2 bill, a $5 bill. There's no $3.57 bill. Darn, right? That would be so not useful. Can you imagine? Lots of things like that in everyday life are quantized. Musical instruments, some are quantized, some are not. A guitar is quantized. You stick your finger and you press the string against the fret and you get a particular note. A violin is not quantized. There are no frets. You can put your finger anywhere and you can get notes that aren't actually notes, right? And that's why a violin can sound so horrendous when you're learning to play. I know because I played the violin as a child. Piano is also quantized. There, you hit a key and you get a note, C, and then you hit the next one and it's C sharp, and you cannot make a sound that's in between those. It's quantized. So Bohr explained this business of emission of light in this way. That, so an electron, say in the first energy level, when it is excited, it absorbs energy and jumps up to a higher energy level. Here we're going to look at, I think maybe this one jumped up to energy level 5. Well, that's not stable, and so that's going to release the energy eventually. It's going to drop down to a lower level. When it drops to a lower level, the difference in energy between the level it started at and the level it ends up at is the energy of the light that's released. The energy of the light is directly related to its wavelength, which we perceive as a particular color. So the violet line that we see in the hydrogen spectrum has a wavelength of 434 nanometers. We can calculate the amount of energy. That corresponds to an electron moving from the 5th energy level down to the 2nd energy level. If one moves from the 4th energy level down to the 2nd, we get the blue-green light line at 486 nanometers. Going from the 3rd to the 2nd, that's a smaller energy change, and so we get a longer wavelength, and we get a red light from that one. Those are the 3 transitions in a hydrogen atom that give off visible light. There are other transitions, but they're outside the visible spectrum, and so we can't detect them with our eyes. Any questions? So we've got electrons jumping. So, electrons are absolutely small, and so they don't obey the regular laws of physics. When an electron moves from one orbit to the next, it is not ever between the orbits. Now, when you go up the stairs, if you're standing on the first step and you go to the second step, for a very brief period of time, you are moving between, right? Electrons don't do that. They're in one level, bang, they're in another level, they don't go in between. Is that weird? Should be weird. It's called a quantum leap. You heard of that old TV show, Quantum Leap? A guy was able to just, travel different places instantly. That's a quantum leap. So the energy of the photon that's emitted, the piece of light, the packet of light that's emitted, is equal to the energy difference between the 2 levels where the atom moved, and we can calculate the energies. So the Bohr model has great historical and conceptual importance, but it actually doesn't work for anything except the hydrogen atom. Bummer, because we liked this one. This one made sense to us, aside from the whole quantum leap business. It's like, okay, we can deal with that one. It only worked for hydrogen, though, so that's a bummer. So why do we even talk about it anymore? Because it gives us a visual of what's going on with an atom. It helps us to understand this concept of electrons shifting energy levels.